So since it's an optimization between, is an interface between statistics and optimization called WISO. So I decided to just give two interrelated talk on sparse learning and distributed PCA. And both of those is trying to realize the same aim. One is to achieve the control of statistical errors and also control of computing resources. In one case is computational complexity for sparse learning. In the other case, mainly is on the the communication cost for distributed PCA. So here are the co-authors. So as you see, there's an end. So there are really two papers. The first paper is still ongoing under submission, I think, with Han Liu, Qian San, and Tong Zhang as co-authors. And it's my understanding that Qian San is there. So I think if you have any questions, probably it's hard to communicate. He's the main driver anyway, so he will be the person to answer. And then the next one is, Dong Wang, Kaizhen Wang, and Ziwei Zhu. So this is really the paper we are wrapping up on distributed PCAs. And again, they are with me here on my side. So if there's any questions, it's them to answer the questions, but let's try again. So here is the outline of my talk. I will first give a computational resources and social error, a general introduction. And then I'll use two examples to illustrate the point. One is sparse learning, and the purpose is to simultaneously control the computational complexity as well as statistical error. And the second one is on distributed PCAs. And the main focus this time is on communication and the statistical error. And then I'll just draw some conclusion based on that. So let me begin with introduction. And this is data tsunami. Everybody's seeing, probably seen a couple of times of this slide anyway. So large and complex data arise routinely from biological sciences such as genomic, genetic, neuroscience, and medicine, and from engineering like machine learning, surveillance video, social media, networks, and so on. So these just to set up a theme of our talk. It also arises from natural science such as astronomy, earth science, and meteorology, or social science. I just came back from Marshall School of Business. So they are all talking about is business and marketing, and certainly there's huge, many big data problems that now be available to them. So big data is everywhere. From internet data to government big data to digital humanities, engineering, medicine, you name it. So there were 5 exabytes of information since creation, between the creation of, between the dawn of the civilization and through 2003. And there were that much information is now created every 2 days. So this according to the CEO of Google, Eric Schmidt, in 2010. So certainly the big arrival of big data has huge impact on on the system such as storage, communication, and computation architectures. And it also has huge impact on statistics, computation, and optimization and privacy. So it's either the data is too big for any single processors to handle, or and so therefore we have to distribute it and store in some other local machines. Or just data will collect hugely at Google scale at different locations, and it's so hard to communicate back to central server or even to analyze a central server. So we certainly face both communication and computation challenges, along with analysis of statistics. And my today's talk is mainly on the interface of statistics with communication resources constraints or computation resources constraints, probably put in less formal way. So these challenges certainly create, a new field, or give a birth of new field now commonly being understood as data science. So driven by applications from marketing to biomedical application, data science certainly has create, many new technology that's challenging all of us, from data acquisition to storage, from big data analysis and to draw, to analyze or to deal with the unique problems from big data analysis to, scientific computing. So this is really a very exciting moment for all of those three areas: machine learning, statistics, and computing. And there certainly have certainly there's a lot of overlap, and we all learn each other, as I can see over the last few years. Statisticians nowadays tend to learn more and more about optimization, and vice versa is also true. So now, what is the ideal dream of statisticians or data scientists? Is certain to create efficient methods that computable in polynomial time and commutable, and of course, ideally also should be statistical methods that is provable. Of course, then adding more and more requirements. In the classical days, we basically just create an estimator, and they have certain kind of statistical efficiency, and we are fine with it. And nowadays, with the arrival of big data, we certainly need to take computation resources such as compressed algorithm as well as communication cost into account. And this talk will be basically focused on, control statistical error plus, computation resources. And the two specific example I use to illustrate the point is sparse learning. So the technique we are going to employ is folded-concave penalized likelihood. And this will give us more efficient statistical procedure, at least in terms of reducing bias and easily to get a strong oracle properties, but at cost of computation complexity. Now, can we derive an algorithmic methods to achieve the same goal? So that will be my first talk. Then the second talk is the distributed PCA. So suppose that we collect a Google scale of data in, let's say, 100 locations, and each location analyze and define principal components or whatsoever for page ranking. And now, how do I aggregate those together? And do I lose information by aggregating in certain simple way to avoid communication costs? So these are basically the talk of my talk today. So let me begin with sparse learning problems. So this is based on a paper, Sparse Learning Control Computational Complexity and Statistical Errors. So that refresh a very good time from memory that I had with Chanson one semester, working very extensively and communicate a lot very extensively on this particular problem. So what is the problem? Well, here is a general, by now probably most people know that sparse learning can be abstract into a generalized penalized M framework. This particularly, I think, starting very early by a paper with Wenzel and also being generalized in a very a big framework by Nagabang and Wainwright and his collaborators. So, so the basic idea is this, right? So if you have a loss function, if I use beta to predict something, if I use parameter beta to predict something, I have a loss, associated with it. And ideally, we want to, minimize the theoretical risk, the expected value of this, but we do not know that, so we have empirical loss. So this L is an empirical loss put in here. Now, in order to encourage the solution to be sparse, so we put a penalty function here. And so the most version number one is Lasso, so in which the loss is quadratic loss, the least square errors. And the loss function is penalized L1 loss. So this is called Lasso. And apparently this framework, include, let's say, negative log likelihood of generalized linear models. Or if you are doing Gaussian graphical models, you could use, or is doing estimation of precision matrix and so on. So you could think in this is as a Gaussian pseudo likelihood. You could put it down here. If you are considering robust loss, you could put in L here as low-bound loss. And even you could put the framework including support of hinge loss and exponential loss in classification. So the penalty, I mean, very popularly studied in statistics is lasso because the whole problem typically is a convex problem. The loss part is convex and the penalty part is convex. So therefore you got a lasso problem. And it was also observed very early on that folded concave penalty such as SCAT and MCP actually work better in terms of statistical error and in terms of bias. So basically, if you're looking at this picture, I mean, the lasso is a very special family of folded concave, right? So it's concave on this side, concave on this side, right? So it's a boundary between convex and concave. And SCAT is concave on one side, so it's a folded concave function, and this is part of MCP. And so on. So this is the general framework that we want to solve. And we want to control the complexity for this problem. And we want to also, with the guided algorithm, to achieve the estimator. So what is the problem and advantage and disadvantage of lasso? So lasso is very fast to compute. By now, we have a lot of algorithms, but it introduced estimation biases as being observed by a number of people. And however signal you have, you always have this log d dimension of errors. I mean, in your mean square error, log d factor in your mean square error, and that can be not optimal when the signal is strong enough. The folded concave estimators, on the other hand, has oracle estimation rates like this without a log d, but this occurs under strong enough, the signal conditions. And then you can even obtain oracle estimator with high probability. So the only problem is that it requires a heavy computation. And even more problem is that some estimator we proved may not necessarily is what we computed. So there's a gap between what you computed and what you proved, right? So theoretical properties has been studied for global minimum or specific type of local minimum. So for example, for finite dimensional inversion 101 or inversion number 1, we basically say there exists an estimator that have that kind of oracle properties and so on. So later on, actually, there's certainly improvement and algorithmic type of methods that was derived to compute estimator and prove this kind of particular local minimum has some kind of statistical properties. So there's also a lot of studies on global minimum properties and so on. So there are also other practical algorithms without theoretical guarantees, such as coordinate descent algorithms, is very frankly very easy to use, but the theoretical property is largely unknown. So the easy way to say is what we compute is not the same as what we have proved. So there's a theoretical gap, at least in terms of estimator and the methods. So today's talk is to give you an algorithmic approach to this sparse learning problems. So let's look at sparse learning problem again. So we really have two parts, right? So this part is the loss function, which is convex, and then this is the penalty part. And now naturally people were curious. In as early as 2000, right, or even before 2000, we write this paper. So how do we compute that? So without knowing any algorithm at that time, we will just simply do local quadratic approximation to this black scat function or folded concave function. So by derivative here and the symmetry and the origin, so you really determine a quadratic function there. Now we know is a part of majorization and minimization algorithm. Of course, at the time, we could have done local linear approximation too, but unfortunately, if I do local linear approximation, I got the weighted L1 penalty here. At the time, I did not know how to compute, so we use local quadratic approximation. Now, we also have to deal with this part of nonlinear or non-quadratic loss. So once we do local linear approximation, this becomes a weighted loss. And now we have to deal with this part. And this part you can do by the second order methods that Martin Wainwright was talking half an hour ago on that too. And then today, of course, in order to do large scale computing, just like most of people we'll do gradient method. We'll do isotropic local quadratic approximation to this. And then you can solve this iteratively at each step. So this basically give an algorithm looks like this, right? So starting from any initial value, let's say 0 to begin with, right? So you compute your weights function at this initial value. This is local linear approximation coefficients. In this case, it would be a constant if I start from 0. So I got beta 1. So beta 1, because this is constant, really I compute a lasso. And then I compute lasso. Now, once I compute lasso, I calculate my weights again based on computed lasso, and then you calculate beta 2, and now based on beta 2, you calculate beta 3, and so on. Right? So this is really you are solving a sequence of weighted lasso problem or adaptive lasso problem, if you would like to use the words adaptive lasso. So you saw a sequence. It's really an algorithmic approach to solve the Folded-Concave problem. Now, in order to control the complexity, right? So now in solving each of these problems from this lasso to this weighted lasso and the weighted lasso, we naturally ask how many iterations I need to go and how do I solve each of these steps, because it's still a non-solvable problem. And then the second issue is how many steps. This is one step, is a horizontal, and the other step is vertical, right? How many vertical steps I need to stop. And this is really part of our algorithmic approach to this problem. So in order to solve each of these steps, and to make things simple, we approximate this function L beta by gradient method, basically, by isotropic quadratic. So the L beta is non-quadratic. So given your initial values, you just approximate by the gradients plus isotropic quadratic here. And this certainly avoid the computation and storage of a big hashing matrix. And I want to say that even once you do this isotropic approximation, even without doing local linear approximation, as long as you approximate this by isotropic quadratic, even though here you do not do local linear approximation, there's an analytical solution, right? Because it's separable, there will be analytical solution anyway. So analytical solution can be done with or without doing local linear approximation to Folded-Concave penalty. But in this paper, we actually did just for simplicity of the algorithm. And all these methods certainly is related to proximal gradient methods that has been studied by Nesterov, among many other people, and in particular, Lowe and Wainwright, Martin Wainwright have give very thorough study on this. And in order for this, quadratic function to be to majorize our convex function, we require this. The number psi here to be very large, big than our operator norm of the gradient of the hashing matrix at this beta 0. That would be a nightmare to compute if we do that. First, this is large coherence matrix, large hashing matrix. Second, calculate the operator norm of such a large matrix is very, very intensive. But fortunately, you really do not need that. You really need just to do local. You just really need to do just local majorization rather than global majorization. And this kind of parameter psi can be easily obtained by the line search. So in other words, when we really study of majorization and minimization algorithm, so we all just like this is a function you want to majorize. So if I do local quadratic or local linear, it's a majorization. So this would be a majorization algorithm. But if you look at the proof that required where majorization is used, all you really need to use is that the next step move of your target function is majorized by, is no bigger than the function you majorize. So you really only need this local property. As long as this local property is satisfied, the whole, decreasing property of target value will be valid. So for this reason, people use this isotropic quartet approximation along with line search easily to get the next value of size. Okay, so now here is really a little bit more detail of our algorithm. So you start from initial value beta 0. So you compute the adaptive weights, right? So you can compute adaptive weights. In this case, of course, constant for this penalized function here. Now you solve this. Weighted L1 problem for this particular weights, right? And this is solved by using, the proximal gradient method, or by using gradient methods to solve this. And now with beta 1, you do the same thing. You compute this new lambda, the adaptive weights, and now solve this again by we call local approximation of majorization and minimization algorithm. So in detail, so this is really the algorithm. So we start from very early initial value, very far away from any region of our interest. So you do optimization, which is really solving lasso with optimization error we call epsilon c. Epsilon c is the optimization error. And we were hoping computing this a little bit rough, but accurate enough for our second step. So from second step to the T step, we will require optimization error to be of a smaller order, like epsilon t. So in other words, the initial stage optimization error would be bigger than the later stage optimization error. And for Gaussian case, this is really the order that we choose. N is the sample size, D is the dimensionality for initial estimator, and this will be the in the second stage contraction state, and we'll see what we call contraction state and the tightening stage. So therefore our algorithm become very simple. You give lambda 0, right? So starting from initial value, you use this local approximation of majorization minimization LAMM to calculate the initials one step, two step, and compute until iterating this this isotropic quartet approximation to our problem K1 times, and K1 is proportional to the estimation error that you have here to this quadratic term. So this step would be the longest you compute, because you are starting from a very, very crude initial value to get into some solution with certain kind of sparsity. Now, once I got this, solving this beta 1 tilde is approximate solution to lasso. So, and we have always stop exact at the number of step here. So the number of step here, it becomes n squared, or 1 over n. And then from that step, you now get a new beta 1, you calculate new weights, right? So for this new weights, you solve optimization problem. Each of these optimization problem, you use LAMM iteration to solve this. So each of these weights solving one of, each of the row that is solving from one step here to here, basically it's just solving this problem. Right? So each row here is really solving the optimization here by using gradient methods, and so on. And then we do this t times, and t doesn't need to be very large. Indeed, need to be very small. Of log d order. And why is that? So here is the really. We did prove that, but we also use simulation to show that. So initially, you are starting from a very far places, and now you apply lasso in. Because we apply gradient methods to a convex problem. So the rate of convergence is sublinear of 1 over k. So because it's not a strict convex problem, but it leaves us a sparse solution. Right? So it's converged very slowly, but at one point, coordinate get less and less, and let's say to the point, let's say is a third of your sample size, hypothetically, then your problem becomes very strongly convex. So therefore, even though this converge at beginning is at sublinear rates, later on, once you get into enough to the contract region where the problem becomes strongly convex, it becomes sublinear, right? So the second step, once you get to the local sparse region, all the problems there is sublinear. So here, what we're showing is the algorithmic error, log algorithmic error against number of iterations. So this for calculating. The second step is sublinear convergence because now you apply gradient methods to a spot in a sparse region, so where you have strong convexity. So therefore, you converge very fast. And then this is the third step and the fourth step. So you converge very fast. So not after many steps, you achieve your rate. So mathematically speaking, and we'll show more formally, basically saying that the convergence is linear, and because our problem after initial contraction has a strong convexity. So this is basically the graph showing and the algebra showing the statistical error and the iteration effects. So we start from somewhere very remote away, and we keep applying approximate lasso until I bring to a certain region. At a certain region, my problem becomes sparse enough, and therefore my problem becomes a strong convex problem. So even though I use gradient methods, so it getting, the convergence getting, algorithmic convergence getting very fast. And so each step from beta 1 to beta 2 is very fast because you have linear convergence. From beta 2 to beta 3, you have linear convergence. And from beta 3 to beta 4, you have linear convergence. And at certain step, there's long diminishing return when you are inside statistical convergence region. No matter how you're trying to tight, the error will be the same. So this is probably better seen by seeing this statistical property. So by seeing this statistical property for so the previous estimation error to current estimation error has a statistical error here plus some contraction effect delta here. So you could imagine in the initial few steps, let's say in the first step, this error is very big. So the estimation error is completely controlled by this initial estimation errors. But after iteration enough, because this contraction exponentially fast, so this initial effect will be gone. But this statistical error will remain there. So after a certain while, iteration doesn't improve anymore, but it's also tell you iteration doesn't deteriorate either, right? So in other words, once you get to contraction region, iteration doesn't deteriorate either. So this is basically our results. Now we put our result in a little bit more formal framework, right? So this is local sparse eigenvalue definition. So definition is very similar to what they've defined in the literature. So this is for a hashing matrix, you are calculating the quadratic form, right, subject to the non-equal to 1. And that vector have to be sparse, no bigger than m. Everything is the same, except now we're asking that we are only analyze this locally on beta rather than for all beta. So we only require beta is in a local neighborhood, L2 local neighborhood of the true parameters. So similarly, we define the minimum eigenvalue by take inf here rather than take sup. And so this is the just definition. And we really require, local, restrict eigenvalue condition. So let S be the number of non-sparse elements of true parameters. And suppose that my R, that the radii that I use here is bigger than this number. then we basically assume that the ratio between these two is bounded from below and bounded from above. So with this condition and the minimum signal condition, the signal is bigger than the thresholding, and then of course this usually satisfies for all those gap and lasso. So as long as your tail behave like L0, then we can really show the contracting results that I showed you before. That is each step have this kind of convergence. So the previous step and this step's statistical error is being contracted by amount of delta that less than 1, and then plus statistical error here. And if you take t to be big enough, you can easily just, this iteration is very easy to solve. You can see that the statistical error will be achieve the oracle rates of convergence. And here are two simple remarks. The first one is that the result really determines, just like Martin Wainwright and his collaborators type of results, is determined as long as your regularization parameter satisfies certain condition, this kind of result will holds. And if you just consider L equal to 1, which is really Lasso estimator, so Lasso estimator will achieve certain rates like this, and this is not really accurate enough for you to do like a post-Lasso or so. So in other words, the problem cannot easily be solved by using post-Lasso. And then, as I explained to you before, at initial step, we don't have strong convexity. We have only convexity, so the rate of convergence is sublinear, so it requires this many of LAMM type of iteration. And after a certain while, it becomes strong convex. So therefore, therefore you have exponential, linear rate. So that's why you require only logarithm order of this. So if I add in these two according to our required accuracy of optimization error at initial step and at final step, we will get, the number of iteration required is more or less of order n squares. And so even though initial estimator is cruder, so most of computation is spent on computing lasso. It's not really spent on improving estimator to achieve oracle rates. So in other words, if you write code properly, the calculation of lasso and the scat shouldn't be much, at least in terms of computation time, but you can gain statistical efficiency. So this basically what I would like to say for the first part. So we basically propose an iterative LAMM algorithm that provides a statistical optimization algorithm to solve non-convex optimization problems. We examine the iteration effects and the optimization error effects. Indeed, we even examine more general optimization error effects. I didn't show here just to make presentation easier, but they are on the paper. So we propose weaker conditions which only require local analysis. That's we introduce a device, a trick by combining convex and the local analysis. We could avoid some global conditions or that people impose on the estimation error on the optimization problem. And we show basically all approximate solution to our problem enjoys all statistical rates of convergence with controlled algorithmic complexity. How many times we are calculating I-LAMM, we know exactly how many times, and each of these have very limited amount of computing because they are very explicit thresholding type of things. So this basically my first talk type of talk, and now let me move to the second subject, distribute PCA, and this is based on the work ongoing. We haven't quite finished yet. On Dong Wang, Kaizhen Wang, and Ziwei Zhu, who are with me here. So let me say what is the problem, right? So the principal component analysis. So that principal component analysis are very fundamental tools, right, for statistical machine learning, and that was covered also quite extensively by Martin Wainwright, even though he used random projection to achieve similar things, but nevertheless, is a fundamental tool. It's for either it's for dimension reduction or for summarized data. And someone like me who has been worked so much in finance or genomics, for me, it's also used to discover the latent factors for us to do many other good things. And when you have all data together, there are lots of studies on this, right? So let's say the principal components, the first eigenvector can be estimated with rate of convergence depending on dimensionality and the sample size, and then the eigengap. So this is very analytic and explicit. It has been studied by many people. Starting from Debashis Hall and Ian Johnston's group, Danshan and Steve Merron and our own group. So they, just published in 2017. So for those people who want to know detail, it's certainly there. Now the issue is when data is too big, like Google, or data being collected in different locations, or when you have, let's say, billions of features. That's when I stay in Baidu every day, they're talking about billions of features because of interaction of words. Now we have to do distributed compute PCA. So what can we do with distributed PCA? So here is our problem setup. So I assume that you have capital N samples stored on M different servers. So you store on this M different servers. And for simplicity of our presentation and study, I assume data are sub-Gaussian with covariance matrix sigma. So in other words, I assume data are homogeneous in each. And we are aware this cannot be homogeneous. So we extend this to heterogeneous covariance with certain kind of homogeneity, sharing some kind of homogeneity. That would be that would require some effort to expand. And so for presentation, I assume that all these local data are homogeneous. So they all admit singular value decomposition or special decomposition here. So our interest is not to estimate all eigenvectors, but just to estimate the top k eigenvectors. Let's say top 3 eigenvectors. And we measure the statistical error by forbiddenness norm of these two, which is really sum of cosine of principal angles between these two eigen spaces. So here is the algorithm that people typically use. So you have, for the first local machine, you have data, you compute your sample covariance matrix, you compute your principal components, let's say top 5 principal components. And for the M machine, you do the same thing. Each machine send that top k principal components to the central server, and the central server compute this low rank, right, rank k, average covariance matrix there, and then using PCA to extract this as an aggregate estimating of this. So this kind of distributed PCA has two advantages, right? So first of all, privacy being preserved. Nobody ever seen other people's data, ownership being preserved, right? So everybody only sent PCA then, to the central server. Nobody ever seen any other people's data. And that make it feasible when you have many hospitals, each hospital collecting a lot of their patients' data. If you ask them to give out the data for you to analyze, even that's possible to aggregate, is impossible to, in practice, for people to hand over the data to you. So this way, this kind of simple algorithm has very simple, has one big advantage. Everybody with nobody, central server, nobody ever touch any other people's data. Now the communication cost is we only communicate top k eigenvector, let's say top 5 eigenvectors. So the communication is limited. Rather than communicate D square matrix over, we only communicate a couple of eigenvectors. And why do we aggregate this way? So this is really the sample average. These two steps is really the sample average in the manifold, right? So if I ask myself, say, hey, I want to find a centroid of eigenspace so that it closest to all those M different eigenspaces sent by each individual machines. So I want to average those eigenspaces. You will naturally minimize the Frobenius norm of these discrepancies, and subject to the fact this matrix had to be orthonormal. So the solution would be exact PCA of this matrix. So in other words, the last operation is really an extended sense of extended sense of averaging in eigenvector space. And now people naturally worry, right? So suppose I want 5 principal components, but the top 5 principal components may have some called spillover effect, right? Economists will call a spillover effect. So in other words, some of those dimensions will go to 6, go to 7, go to 8, right? So it could be spill over to other top eigenvalues. Well, in this case, you can do this, right? So you could just send, let's say, type 10 eigenvector over, right? So you are interested in 5, but you ask each machine to send 10 over to the central machine, and the central server compute this and then take top 5. We'll show that the result actually a little bit improvement, but due to signal to noise ratio, the improvement is very little. But this certainly can solve a spillover effect problem. So now how does this kind of aggregation work? It's a very simple communication conscientious method. How does it work? So let me talk a bit on bias and variance of this kind of issues. So recall that each machine sends in their top k eigenvector to the central server. So central server just average of this sample covariance matrix, right? And average these sample covariance matrix, and these sample covariance matrix, technically speaking, by law of large number, you expect to converge to expected value. So therefore, I denote expected value of each machine's expected value of each machine's sample covariance matrix as sigma star, right? So sigma star is not sigma; it is just the expected value of this matrix, because later on we are aggregate at this level. So Vk star would be correspond to the top k eigenvalue of this, right? So now by using triangular inequality, I could insert Vk star here is our target, right? And the Vk star to the true Vk. So we achieve bias variance decomposition. So the first part is random because this matrix is random, right? So so this part is really very similar to like sample covariance in our mean square error decomposition. And this part, rho is Frobenius norm, by the way. And this part is the bias, right? So is the matrix, the top k eigenvalue of sigma star rather than top k eigenvalue of sigma. So this part we call bias. And you expect bias to be small because by law of large number, if I have enough m here, this guy will go to 0. And this is really a formal calculation what we made for variance terms, right? So the analysis of sample variance terms, which is basically this term, right? So is our, for each individual machine, how this can be deviated away from its expected value, right? So how this can be deviated from its expected value. And we basically are saying the Frobenius norm of this matrix, and if this is a random variable, if I take sine norm of that, you will have depending on operator norm of your sigma, and then this is the eigengap, k is number of top eigenvalue, and then this r is something we call effective rank. Indeed, it's a little bit smaller than effective rank. Effective rank is square putting inside. We are putting square outside, a little bit smaller than effective rank. So this is basically showing you how different each individual machines, because each individual could still have a lot of data, could still have n data. So how those n data's eigenspace or created a sample covariance matrix deviated from its expected value is of this order. And here psi norm, I didn't define psi norm here, but basically at the layman language, so if I say psi norm is of certain order, this really means this random variable or random quantity is of this order, and in addition to have exponential concentration. So it is much stronger than the big OP that we normally see. Not only you need a big OP, but also you need exponential concentration. So this basically say we have exponential concentration in addition to have rates of convergence like this. Now, when I aggregate m of those together, right? So v tilde is this, right? So v tilde is the eigen the eigenvector, the top eigenvector of this aggregated matrix, right? So when I aggregate m of those, so you expect the whole thing to be smaller by an order of m, and this is indeed true. So therefore, really this quantity acts like pretty much like a sample covariance matrix. And we also do the analysis of bias, and the analysis of bias is a little bit tricky. So this is the bias, right? So this is the VK is the one what we want. VK star is the one we actually estimated, and we want to see how big the discrepancy between these two in terms of Frobenius norm. So in order to recall how we do operation, so we basically do this, right? So for Lth machine, you calculate sample covariance matrix, you apply PCA, and the PCA get the top k eigenvector. So you reconstruct the covariance matrix, you take expectation, we define this as sigma star. Now sigma star, you apply PCA to get top k PCA, so you got this. So this is how we got VK star. And the VK, the same, you're starting from sigma L, and now you just take expectation, so it's really the true sigma without this PCA step, right? And now you apply PCA, you got this VK. So these are operations very similar, except the first one have one extra step of this, right? So natural question you may ask is when these two quantities are the same. So if they are the same, then it's unbiased. And fortunately, we were able to see for a very large family of distributions, it is unbiased. And this is the distribution we define. So if a vector, d-dimensional vector called symmetric, meaning that if I just change one coordinate from positive to negative, so their distribution are identical. So it's basically saying the density is of square of each elements. So this is density. Density is symmetric, basically. So this is the definition of symmetric. And then we say, well, a vector x has covariance, right? It's non-identity mean have covariance like this is symmetric. Has symmetric innovation, which really means that if you spherize this distribution, right? So you make this distribution, let's spherize this distribution, then distribution is symmetric. Right? So basically, for all elliptical distribution, it will be symmetric. For any distribution that you see reasonable is symmetric. So this is the family. And we have a theorem basically saying that if X has symmetric innovation, then the sigma star that we calculate in the intermediate step and the sample covariance we calculate has the same eigenvectors. And in particular, if the sample variance is not too big, then the problem is unbiased. So here I should remind again what sigma star, right? So sigma star is our intermediate step expected value, right? So you from your PCA, you sending your top k PCA, you calculate expected value of that top case PCA we define as a sigma star, and so we basically have shown that the set of eigenvectors are the same, and we need a little bit additional condition to say that the top k eigenvector are indeed the same. So this is really unbiasedness. And now if you are unwilling to assume certain kind of symmetry in your innovation, like as we generally define here, then you have to do Taylor expansion and the perturbation type of arguments, right? Recall that uh, VK is the top K eigenvector of this, right? And VKL is top eigenvalue of the K's computer, and this is the top K eigenvector of the population, is population version, right? So if you do thinking this as a function of this, right? So this as a function of this, thinking of quadratic Taylor expansion, it would be this guy approximate at this guy, and then plus linear of these two elements, right? And then plus quadratic of this element, just thinking heuristically. Now you take expected value of this. So this would be sigma star, this would be itself, because each of these are unbiased due to linearity in this. So this term will be gone, so you automatically get a quadratic error in this approximation. So using this trick, we could rigorously prove that for general case, the bias could be analytically bounded by some quantity like this, again, depending on eigengap, effective rank, operator norm, sample size, and so on. So if we put all those together, we conclude our mean square error, right? So for symmetric distribution, I have no bias, so I have only variance term here. So this is really getting the same rate of convergence as the full sample. Principal component analysis. And for general distribution, we could show, there exists universal constant. The first part is the variance part that we analyzed already. The second part is the bias part that we analyzed already. And in order for bias to be negligible, your M, the number of nodes, cannot be too large. And all this has a catch. We need the local sample size to be reasonably large, and have to be big like this. So we basically saying this, right? So we will obtain the same rates of convergence as principal component analysis as if the whole data is available to you. So this is the first conclusion we actually get here. And then the second conclusion we get here is basically saying that we need the minimum sample size in each machine. And this is a little bit coming from technical, but we actually were able to calculate or construct another example. If you have sample size below this, then you cannot obtain the same rate of convergence as the whole sample one. So in other words, the requirement here is sharp. And as I said before, we also extend it to heterogeneous data with certain some kind of homogeneity. So it's approximate heterogeneous type of data. So let me conclude with just one simulation, probably provides you a lot more insights. And the simulation is that I have n server, and each node has n data. They are coming from normal. So they have not covariance matrix has 3 spike eigenvalues. So k equal to 3. The principal component would be the first 3 coordinates, right? And eigengap would be 4 lambda minus 1. And the lambda we choose similar order with the d. And if we're now looking at the statistical error of our distributed PCAs, so this is really the rate of convergence if we plug in everything into it. So in our calculation, whenever we calculate mean square error of these terms, we calculate everything based on 100 simulations. So we do this for many different configurations of n, delta, m, d, and so on, right? So this is the first one we examine the statistical rates of convergence versus m. So this is really the log m that I plot here, right? So this is for different kind of sample size in each machine, from 500 to 4,000. And this is for different dimensionality from 100 to 1600, like 100, 200, and so on. So you can see that all of those, go to 0. Except for the rate at the rate of square root 1/2 rates. Right? So we prove this. We also verify similarly fixing other variables like a sample size or some D or delta, all those rates we verify having identically the same rates. Now, it's more interesting is that we are consider like taking all those factors into account, right? So this is the accuracy for being known of our distributed PCA to the true PCA. So it certainly depends on sample size, dimensionality, number of node, sample size, and eigengap. And we run this regression, right? So based on different configurations. And surprisingly, all those coefficients surprisingly close to 1/2, right? So all those 1/2, this beta should be 1/2, right, and so on. So it's dimensionality here, so it should be positive 1/2, as we can see from here. D is have the exponents positive 1/2, and so the range is surprisingly close. And the multiple R square is basically 1. So therefore, if you plot fitted value against the other value, is basically the same, right? So this is really the fitted value against observed value is 100% correct. So basically it means that our theory predict the case very accurately by combining these two results. The last one, we were just testing a case that trying to say, hey, our distributed PCA, how does it compare with full sample size PCA? How does it compare with full distributed PCA by adding 5 extra eigenvectors, right? So this is to protect against spillover effect, right? So this is to protect against spillover effect. And we plot all of those three here together for lambda equal to 30. And you're barely able to see the differences performance among those three methods. So in other words, our simple distributed PCA work as well as partially communicated, right? Protected distributed PCA or whole sample PCA. So the error, statistical error, is barely able to see any difference. So in other words, I can conclude there are very little spillover effect. So here is the conclusion that I draw, and I think it's about time. So the distributed PCA is unbiased when the innovation is symmetric. In general, bias can be controlled as long as the M number of node is not too large. Distributed PCA has aggregated variance effect, and it's enjoy the same performance as PCA on the full data. And that's all I want to say. Thank you very much.